ORDA Science Webinar 101 Series. Passive Sampler Options and Advantages. Joe Ellen Hink, moderator.
Couple of announcements on upcoming webinars that may be of interest to you. In July, we have a statistics presentation from Richie Erickson talking about moving beyond p-values and NRD statistics. So if you're using half detection limits and p-values for your stats, they're going to show us some different ways. And then in September, we're going to have one of our solicitors talking about science in NERDA cases. When do you need more science data? When is enough enough? And so that will be in September. And then in October, at a date to be determined, but it's looking towards the end of the month, we are going to have a presentation on how oil impacts bird migration. So if you do not receive these email announcements, you can contact Samantha Foster, although she's out on leave right now. So we'll drop in the chat who you should contact, but you can certainly contact me and we can get you on that email distribution. And then just the disclaimer there at the bottom that the findings and conclusions that are in the webinar do not necessarily represent the views of the DOI NERDA program, the department, and so forth. So the attorneys are happy now with the disclaimer, and I am going to now give a brief, I'm going to quit sharing my screen and give an intro to Dave. And Dave, you can start sharing at your convenience. So Dr. Alvarez is the chief of the Environmental Chemistry Branch at the USGS Columbia Environmental Research Center located in Columbia, Missouri. His research focus is on the development of innovative methodologies for passive sampler design and complex mixture analysis of various environmental matrices for emerging and legacy contaminants. As the inventor of the Polar Organic Chemical Integrative Sampler, or POSIS, and researcher on other types of passive sampling techniques, he is widely recognized as an expert in the field and frequently mentors researchers on the use of these samplers. And many of you may have actually talked with Dave or used some of these samplers on your cases. I've seen them used a lot in terms of ephemeral data collection when an event happens. And so I'm really thankful that Dave's taken the time to kind of give us an update on these methodologies. They've come a long way, even in the past decade or so. And so Dave, I'll hand it over to you, but a quick fun fact about Dave is that he has spent the last 13 years involved with recreational soccer with his two daughters, the last 6 of which he coached in his youngest daughter's team. So, hey, thanks for giving back on the parent front as well, Dave. So with that, I'm going to go on mute. Dave, make sure you're off of mute and you can get started.
All right, sounds good. Yeah, it was kind of a sad day of reminiscing just 2 nights ago when I dropped off my coach's bag back to the league. And now that my youngest daughter is going to be going into high school, my wife and I are saying, well, we've been coming to this park for games for 13 years and now that's over. We'll be going somewhere else. So, time flies. And with that, time flies also with passive sampling. And I'm going to give you a little bit of a history and kind of really start you off with some of the basics. I know some of you probably have used passive sampler. Some of you may be familiar. Some of you may be joining because you're wondering what the heck are these things I've heard people talk about.
Passive sampling technologies. What are they and how can they help with assessment and restoration efforts?
So with that, we'll go ahead and start going through some of this. And again, towards the end of this, I'm going to kind of share some case studies. Just kind of show how the sampler has been used in real scenarios, a couple of which are, some different cases. But I want to get everybody kind of at the same starting point, at least so you have an understanding of what I'm talking about before we actually get into the examples. So what is a passive sampler? Simply, it's an abiotic device that's used to sample chemicals from the environment. There's samplers that are designed for sampling almost any environmental medium, air, pore waters, sediments, surface waters, groundwaters. But typically, when you see these in the literature, people are generally talking about sampling of water and or air. The devices are considered passive because they have little to no moving parts. They don't require power to function, and they sample over prolonged periods of time, which, depending on the type of sampler you're using, that could be anywhere from hours to months to possibly years in an example I'll show later.
Passive samplers. Why use them?
Passive samplers can offer advantages over other types of traditional sampling techniques as they allow for the concentration of trace but potentially toxicologically relevant mixtures of chemicals over time. And the samplers function in nearly all environmental conditions regardless of water quality. If you are trying to do some sort of contaminant assessment where you're wanting to look and use organisms as your metric of exposure, some sites just may be so contaminated that organisms are not going to survive there. Maybe the conditions just aren't quite right to where they don't really want to live there. So it's hard to find the animals to collect the sample. Passive samplers just kind of do their thing, and they don't really care what the water quality conditions are. Surface water is probably the primary application, although we do see quite a bit of work in groundwater and pore water, and there is air sampling techniques that are rapidly growing. Depending on the type of sampler that you're using, passive samplers concentrate chemicals from large volumes of water, anywhere from tens to hundreds of liters over that deployment period that they're exposed, which results in increased sensitivity and lower detection limits that may be possible with the traditional sampling techniques, such as going out and taking a grab sample of water. Results from a passive sampler are often expressed as the time-weighted average concentration of that chemical, which then can be related back to ecological risk assessments to help determine potential exposure. Passive samplers only dissolve chemicals, or passive samplers only sample chemicals from the dissolved phase. Chemicals that are bound to suspended sediment, colloidal material, or what forth will not be sampled. The dissolved phase therefore mimics an organism's exposure through respiration and direct absorption into the body. A popular advantage is that since these samplers are deployed in an environment over prolonged durations, it increases the possibility of capturing episodic events such as a spill or stormwater runoff event that may be missed if you're just doing routine, instantaneous type of sampling, such as grab sampling. This is especially important when you're sampling in remote locations where getting to a site quickly to capture an event could be difficult. Although an episodic event may be captured by a passive sampler, remember the data is expressed as a time-weighted average. So the maximum concentration of that chemical during the event or the timing of the event can't be determined.
Comparison to other techniques. Grab/discrete, composite, and passive. A chart shows the concentration peaks and valleys that may occur and how an encompassing passive technique can overcome grab and composite sampling issues. A red line halfway up the chart illustrates time-weighted, average, concentration, and a dotted MDL line falls slightly below the red line.
This figure is a bit complicated, but it shows the differences between sampling techniques and the potential for detecting the chemical. To kind of walk you through it a little bit, looking across the x-axis, you see peaks which represent changes in the chemical concentration over time. The dashed line represents a potential method detection limit for the analytical measurement. Depending on when a sample was taken, you may be at the maximum of a peak, and I'm not sure if you can see my pointer, but the maximum peak here by this little arrow represented on the left, or you may have come back a day later and that peak has already went downstream, and now you're back to baseline conditions where you would have missed it. Another technique that's used sometimes by doing multiple sampling or some sort of automated sampling is coming up with a composite where you're collecting multiple samples over a time period, combining those into one. In that case, you can see you're sort of collecting around these changes in concentration, which increases your chances of being able to measure it. With the passive sampler, again, you're sampling over this entire time period. Here, integrating across multiple events represented by these peaks. And although, again, we don't know what those maximum concentrations were, you can see by that red line that that time-weighted average concentration is measured. So at least you have that likelihood that you've measured that event, that it occurred, and can say a little bit of something about what's happening at that site.
General types of passive samplers.
When you talk about passive samplers, at least as far as how they fundamentally work, they generally fall into two groups, either equilibrium samplers or integrative samplers. And it all depends on where they fall on the uptake curve that you see in the bottom right-hand corner. This curve is a typical first-order uptake curve. And as you can see, it starts off in a linear phase, which is your integrative phase. And then it goes and approaches an equilibrium. Equilibrium samplers typically have shorter exposure times in the environment, and they have a very low capacity for accumulating chemicals, which is critical for them to reach equilibrium in a reasonable time frame. Data from equilibrium samplers typically represent the latter stages of the deployment as they are constantly adjusting to the current conditions, trying to maintain that equilibrium. Their equilibrium samplers most often are used for groundwater, sediment pore water, and air sampling, although I have seen some surface water applications. Common samplers that you may come across that tend to operate more as equilibrium samplers are the solid phase micro-extraction fibers, the SPME or the SPMEs, polymers on glass, and different types of diffusion samplers. Integrative samplers have a much higher capacity to accumulate chemicals over time, which results in being able to use them for much longer exposure periods, getting into weeks to months or longer. An integrative sampler can act as both an integrative and an equilibrium sampler at the same time. For example, a chemical with a low logged octanol water partition coefficient, or a log low, KOW, will reach equilibrium much faster than a chemical with a high log KOW. So could be similar chemical classes. We'll take PAHs, for example, some of these petroleum hydrocarbons. Something like naphthalene is going to reach equilibrium considerably faster than something like chrysene due to the differences in their log KOW. While the sampler is working in that integrative or that linear phase, the data is expressed as the time-weighted average concentration. These type of samplers are most commonly used for surface water and also for air applications. Common samplers are the SPMD, the POSIS, ChemCatcher, polyethylene devices, or silicone strips, and there's many others as well. Three of the more commonly used passive samplers for organic chemicals are the semi-permeable membrane device, or the SPMD, polyethylene devices, PEDs, and the polar organic chemical integrative sampler, POSIS. The SPMD has been used globally since the early 1990s. It consists of a lay-flat, low-density polyethylene membrane tube that's filled with a neutral lipid, which is triolein. It's a common triglyceride that's in most vertebrate organisms. The SPMD is designed to sample neutral hydrophobic organic chemicals, typically with log KOWs between 3 and 9. So when we think about a lot of the organic chemicals that have been used over the decades and are the ones that tend to be regulated, those typically fall in that KOW range and are sampled by the SPMD. PEDs are similar to SPMDs in the types of chemicals sampled. The difference is it does not contain the triolein. It's very similar. It's the same type of membrane polymer. It just doesn't have the the lipid. When comparing the mechanisms and uptake, they operate the same way, but PEDs will have a lower capacity for retaining chemicals over time because it doesn't have that extra lipid reservoir. Whereas the SPMDs and PEDs sample the hydrophobic organic chemicals, the POSIS was designed to sample the hydrophilic organics. So chemicals typically with log KOWs less than 3. So those more water soluble things that we were missing with those other samplers. The POSIS consists of 2 microporous polyether sulfone membranes that envelopes a solid phase extraction resin that traps the chemicals. The composition of that resin can change depending on the application, depending on the types of chemicals you're interested in sampling. But typically, Oasis HLB is used, and that's one of the more common resins used in environmental sample processing anyways. There's been many types of chemicals measured in SPMDs, PEDs, and POSIS. The most common chemicals can be grouped into either those legacy or regulated chemicals and the current use chemicals. And you can kind of see here, where those break out. The legacy or regulated chemicals include your polycyclic aromatic hydrocarbons, the PAHs, your polychlorinated biphenyls, PCBs, the polybrominated diphenyl ether flame retardants, the PBDEs, and your typical legacy chlorinated pesticides such as DDTs and chlordanes, as well as dioxins and furans. Current use chemicals tend to include pesticides currently in use, and a lot of chemicals that you would think of coming from wastewater treatment plant effluents. So pharmaceuticals, hormones, fragrances, and of course, now with the interest in PFAS.
Exploded view of the uptake process. Cross sections showing how collectors absorb particles. The left image is the SPMD, and the right is the POCIS. The SPMD has lipids on the interior with a honeycomb-style membrane, and the POCIS has a thicker, more open membrane.
I'm not going to really go into the details of uptake much, but just to kind of give you a quick idea of what happens for the SPMDs and PEDs. Looking at the figure on the left, chemicals partition into that membrane. Polyethylene is a non-porous membrane, which means there's no physical holes. And you can see those little white ovals. What those are cavities that are formed in the polymer chains, and chemicals can move through those cavities to get into the lipid layer on the inside. A little bit different with the POSIS. The POSIS uses a microporous membrane, so there are actual water-filled pores, 0.1 micron in diameter, and chemicals typically are going to move through those water-filled pores inside the sampler to where they get trapped on that resin. Although you do get some chemicals that do tend to partition through the polymer matrix as well.
Passive sampling for metals/inorganic.
The use of passive samplers for metals is an established practice. I personally have less experience with those, but there are options available, just not quite as many configurations of samplers as what you see on the organic side. Most of the research with passive sampling for metals tends to revolve around the sampling of pore waters, but there has been work done with surface waters as well as atmospheric deposition studies. I'll go through a couple examples of sort of the main metal samplers here. The first one is the diffusive gradients in thin films, or the DGT. This is a popular sampler for measuring metals in surface and pore waters. It is a commercially available sampler, which kind of leads to its popularity. The DGTs consist of a filter membrane that protects a rate-limiting diffusive gel, and then underneath that, a gel that's embedded with a chelating resin, and that's where the metals get trapped as they enter the sampler. There's a configuration of the DGT that's a sediment probe that you can see on the pictures on the right, and this allows to be able to measure profiles of metals at the sediment water interface, as well as that by depth within the sediment. A common sampler for measuring metals in pore water is the peeper. Peepers can come in different forms, but typically they consist of a reservoir containing deionized water, which is separated from the external water by a dialysis membrane. Using frames with multiple sampling cells, such as the picture on the top right,
Sample collector is tall and narrow.
allows you to determine some sort of depth profiles of metals in contaminated sediments. Again, uptake is based on that diffusion of metals across that membrane as they tend to try to reach equilibrium. Okay, the sampling efficiency in peepers is determined by the equilibrium time and the diffusion coefficient of that chemical or that metal across that membrane. Another sampler is the stabilized liquid membrane device, or the SLMD, which was developed by USGS as a research tool to measure cationic metals in surface waters. More recent developments has been using this sampler to measure metals at the sediment water interface, and I'll show an example of that later in the presentation. This sampler is constructed of a lay-flat polyethylene membrane, the same one that was in the SPMD and the PED samplers, and I apologize for all the very similar acronyms here. But the difference is this sampler has a metal binding agent in it that forms a liquid phase on the surface of the membrane. So when metals interact with that liquid phase, they become trapped. This phase is stable, allowing the samplers to be deployed for several weeks and then stored for several months before processing analysis. At that point, it's a very simple acid extraction, and then they're ready for analysis by common methods. The last type of sampler I'll show you is focused on atmospheric deposition of ionic species. This is samplers termed ion exchange collectors that use both cation and anion exchange resin beds to sample and retain a variety of ionic species. These have been used in remote locations in the Arctic over long exposure times, like throughout the winter, to measure low concentrations of various species through deposition. There are many other types of passive samplers for measuring chemicals in the air, both for organics and inorganics. Much of this work has a foundation in the industrial and occupational health area, where passive monitors are commonly used to determine exposure to human workers. Are they being exposed to solvents or whatnot? Substantial work has been done to adapt those technologies into environmental air samplers. There are actually some global networks that exist for monitoring, especially organic contaminants in the air. But I won't get into that in this presentation. So initially, passive samplers for environmental monitoring studies were developed as a surrogate for biotic sampling. Considering the inherent difficulties of capturing some biotas, such as fish, and the work required to process and analyze those samples back in the lab, the passive samplers do offer some advantages. One is that the passive samplers don't move, so you're assured of collecting a sample representative at a specific location, as opposed to a fish that you don't know how much in a region it's moving around. Issues of metabolism and excretion of chemicals are not really an issue with these types of samplers. However, depending on the chemical and the type of sampler used, there can be degradation or release of some sample chemicals that occur. And I'll touch on that in the next few slides. There's no need to analyze multiple tissues to obtain the full picture of exposure. We've all heard that, and we're aware that some chemicals, if I think of pharmaceuticals, an antidepressant is going to interact with the brain. Other chemicals will go to other organs. We see the same thing when we're analyzing different tissues for example, a fish. Understanding where in that body a chemical may end up is important to make sure you get an accurate analysis. However, it is remember that, again, we're working passive samplers. We're only sampling from the dissolved phase. Therefore, they cannot provide an assessment of exposure due to particle-sorbed chemicals, which may occur through feeding. So when you're doing that organism to passive sampler comparison, there are some differences. Some of which we can see here in this slide, and this is admittedly it's a busy chromatogram here, and you don't need to know anything about chemistry, but if you look at this chromatogram here in the black on the left, the top is the analysis of a mussel, the bottom is the analysis of an SPMD, both from the same site where we're looking for chlorinated organics. What you can see from here is on the SPMD in the first half of this picture, there's a lot of peaks, all of which represent different chemicals. Because it's in the early part of this chromatogram, they tend to represent the lower molecular weight, those lighter chlorinated organics. You don't see as many of those in the mussel, which tells me that either there was more rapid excretion of these chemicals, or maybe there was some metabolism of these chemicals by the mussel. The other thing that we see is the mussel tends to have bigger peaks in the second half of the chromatogram that we really don't see from the SPMD. Those are ones that are the heavier, the higher molecular weight chemicals that most likely were more associated with particulate matter that then was retained by the mussel that would not have been sampled by the SPMD. However, if you start looking in that sweet spot where you have that log KOW kind of between 3 and 6, 3 and 7, that works really well for an SPMD, and that would be sort of the middle of this chromatogram, you see things that start to be a little more similar, which you can look at the bar graph on the right, which is 4 representative chlorinated pesticides, and you can see that the relative abundances of the different pesticides are pretty much the same, at least in these examples. This here's another example of where SPMDs and caged fish were collected and analyzed for PCBs. This particular graph is a principal component analysis, and it shows that the clustering of fish and SPMDs was in fairly good agreement, which indicates that the SPMD was a suitable surrogate for measuring PCB concentrations that would have ended up in this particular fish species. Some passive samplers, such as SPMDs, have a lower elimination rate constant compared to biomonitoring organisms, which can have a major effect on the retention of chemicals over time, especially those absorbed during episodic events. Again, we're looking at SPMDs, and this time clams in the top figure, and you can see for the pHs, over time the clams had much lower concentrations of the different pHs that remained. Doing some modeling, looking at first order residence time for a typical pH, in this case fluorine, you can see that in the lower figure that you'll have detectable levels of fluorine left in that sampler in the SPMD over at least a 2-month period. You should be able to still detect something, as opposed to the oyster, where after about 15 days, pretty much all detectable levels, or at least definitely after 5 days was below the detection limit, and by about 15 days, levels were back down to baseline. So if there was an episodic event, you do have a defined time before that event would have been lost in these types of samplers. So we're all used to having a sample analyzed and getting a concentration of a chemical. Although that's informative, it doesn't tell us anything about if that concentration is important. With increasing frequency, environmental health assessments become a multidisciplinary bringing together experts from across the sciences to answer these broader questions, answering that so what question. On a smaller scale, we're seeing an increase in using results from chemical measurements to help inform biological observations. This is often in the form of some sort of testing of extracts using a variety of either in vitro assays to identify effects on a specific biological endpoint. But then there's also in vivo experiments where whole samples or extracts are either injected into organisms or exposed in some other way to determine the potential effects on a complex living organism.
Performance markers, quality controls, and data. What does it all mean?
So using passive samplers in the field is relatively straightforward. You put it out, secure it, you walk away, you come back after a certain amount of time, take it back to the lab. There's always things that are trickier, but for the most part, it's straightforward. However, passive samplers can be complicated, and as far as understanding some of the different techniques that are important to improve the performance, understanding the quality controls that you'll be using, and how to work with the data afterwards. Depending on the type of sampler used and the chemical of interest, environmental conditions such as flow or turbulence around the sampler, temperature, and or the buildup of biofilm on the sampler surface can have a significant effect on the chemical's uptake rate. These conditions can be highly variable over time, and it's almost impossible to predict how those variables are going to affect at any given point in time. Because of this, users of passive samplers have long recognized there's a need to account for the impact of the variables on uptake kinetics over time. This is accomplished by means of the performance reference compound or PRC approach. And for those of you that have used SPMDs or passive samplers in your study, you may have heard of PRCs. What a PRC is this a chemical that's added to the sampler during construction. And what it does is, while deployed in the field, this chemical slowly dissipates from the sampler. By comparing the amount of PRC remaining in the sampler after deployment to how much you started with, provides a correction factor that you then apply to your uptake models to provide site-specific adjustments, which improves the accuracy of your time-weighted average concentration estimates. Selection of PRCs is an important factor, as first, they need to not interfere with the chemicals that you are interested in analyzing. They need to not be present in the environment because, again, you need to know how much was lost. A lot of times it's recommended to use multiple PRCs to cover a range of fugicities, which is just the ability of that chemical to leave the sampler during the deployment. And preferably, you want to pick PRCs that are compatible with your planned analytical method. We all have tight budgets, and trying to pay for 2 analyses is not always feasible. So careful selection of your PRC chemicals needs to be considered. Lastly, if you are going to use extracts from these passive samplers for some sort of bioassay or bioindicator test, you should not use PRCs. And the reason why is any remaining PRC left in that sampler will get extracted and then exposed to the test, and the PRCs themselves may be toxic or bioactive. So you don't want to confound your results with that. The PRC approach works for samplers that follow isotropic exchange kinetics, which simply is the uptake rate is approximately the same as the deparation or the loss rate. As you can see from this figure here, the 2 curves, they tend to mirror each other. Simplest way to think about this is the sampler is like a 2-way door. As you move through that door, your movement is impeded by the same barriers regardless of which direction you're going. The same things with the passive sampler. As a chemical is trying to move in and out of that passive sampler, regardless of the direction it's going, it still has to deal with any turbulence of water at the surface. It still has to move through that biofilm or fouling layer. It's the same regardless of direction. The PRC approach is not as straightforward, though, for all passive samplers. Those which use a solid absorbent as the chemical retention mechanism, such as I talked about with the POSIS, chem catchers, and there's a few others that are being used. Because of that solid absorbent, they don't follow this isotropic exchange kinetics. So the use of PRCs either doesn't work at all or it's extremely limited to just a few cases. Another concern is with some light sensitive chemicals such as pHs that can undergo photolysis even after they have been sampled inside the device. The polyethylene membrane used in SPMDs and PEDs is transparent to UV radiation, so that UV radiation can penetrate the membrane and degrade the pHs inside the sampler. This is a real problem in shallow clear waters, and if you're doing offshore studies to where maybe you have deeper water but it's clear, but you have a white sandy bottom, it's also a huge issue there because you get a lot of reflection of the UV rays off that sandy bottom right back up to your samplers. Commonly used protective deployment canisters offer some shielding, but really not very much. So there are different techniques that people can use to protect samplers for light. Much easier to do and protect them in a lake than it is a stream or river. Generally, what we do to help monitor for potential degradation is to add a photolysis marker to the sampler during construction, much like a PRC. The one most commonly used is for deuterated dibenzahanthracene. The reason why this one is selected is because it is photosensitive and it's such a big molecule that the only way you're going to see any loss is due to photodegradation. It will not leave the sampler like a typical PRC will, at least not over normal conditions. I mean, it'd have to be very extreme conditions to see any loss. So by monitoring loss of this photolysis marker, you can have at least an idea of whether or not other pHs may have photolyzed or if there was any issues during your deployment. As with any environmental sampling program, appropriate quality controls are essential to ensuring the reliability of results. Some pass-through samplers, especially SPMDs and PEDs, can readily sample air. Therefore, it's important to include both lab and field blanks to distinguish concentrations of the chemicals from the field from potential background levels. It is important to remember, though, that no amount of precaution can remove all traces of background contamination, which is why having blanks to account for any potential background is critically important. It's also important to include some sort of analyte recovery spike to determine the recovery of chemicals during a processing set. This is especially important when working with highly volatile or non-standard chemicals that there may not be a large amount of information to kind of base what expected recovery should be. When working with data from passive samplers, it can be daunting. At first, the data you're going to receive from the lab is going to be, or at least it needs to be, sometimes it doesn't always come from the lab this way, but it should be in the terms of the amount of chemical present in the passive sampler. So you should get something in units, for example, nanograms per SPMD. Although this can be informative, you can still compare sites, you can talk about presence, absence, relative differences between sites. Often the typical goal is to express the data in terms of an estimated time-weighted average water concentration. The methods to get to this water concentration vary in complexity depending on the type of sampler you use and the degree of understanding of the uptake kinetics for the sampler. This can be as simple as a one-step single equation to a multi-step process that incorporates PRCs and sophisticated uptake models. For SPMDs, which is one that has a lot of understanding on and very well-defined uptake models, this is where we start dealing with that multi-step process to get from a sampler concentration to a water concentration. To simplify that, USGS has created some downloadable and customizable spreadsheets that really make it as simple as insert your data from the lab in the yellow cells and the water concentration comes out in the blue cells. But now you have data. So what does it mean? Results from a passive samplers represent the time-weighted average concentration of chemical over that deployment period. The fact that the data is a time-weighted average, it's impossible to know the maximum concentration of events or when they happened in the deployment period, as we talked about earlier. Although it may not be possible to calculate time-weighted average water concentrations for all chemicals that you may measure in a passive sampler, that doesn't mean you still can't get some good information. To be able to calculate water concentrations, you either have to have knowledge of experimentally derived sampling rates for each chemical or have well-defined uptake models that can use different chemical parameters to help perform those calculations. Data expresses the amount of chemical per sampler can still be informative. However, you need to look at your study goals to determine if a passive sampler can meet your needs. If it is absolutely critical that you need to have a water concentration expressed as nanograms per liter or whatnot of chemical X, look in and make sure that that passive sampler is able to give you that type of information. Because, as I said, you either need to know what sampling rates are, or you got to have very good models to be able to do it. And for not all samplers and chemicals is that possible. It's human nature to want to compare data from a passive sampler to traditional sampling techniques. I'm the first one that will say if the two numbers match, I'm going to say, hey, great, look how good these numbers were in agreement. But in reality, it's an apple to oranges type of comparison. All of the data can be similar. One must be careful in making these comparisons, really because of the differences in the information each sampling activity provides. Unless you're doing a rigorous grab sampling regime where you're collecting a lot of samples over the time period, there's no reason to expect that a single data point is representative to the average conditions over weeks to months that you would get from a passive sampler. Not that one is better or worse than the other. All the sampling techniques provide very useful information, and it depends on the question being asked on what type of sample will best provide the information you need. And really, you need to think about these different sampling techniques as being complementary techniques, not necessarily always interchangeable. So in the little bit of time I got left, I'm going to just kind of run through a couple examples real quick. In the months following the Deepwater Horizon spill, there were hundreds of SPMDs deployed along the Gulf Coast from multiple agencies to monitor the presence of pHs near sensitive marine habitats. Depending on the site, the SPMDs were deployed at depths anywhere between 1 and 69 meters. Average depth seems to be about 16 meters from the data that I've seen. This figure shows a comparison between the relative abundance of pHs in deployed SPMDs and that from the floating oils. As you can see, there's a pretty good agreement in the composition of pHs at depth that was measured in the SPMDs compared to that from the floating oils. As part of a response to two separate oil spills on the Yellowstone River in Montana, SPMDs were deployed at multiple locations and multiple time periods to determine the spatial and temporal distribution of petroleum hydrocarbons following the spill. This data was used along with observations from captured fish to determine the potential exposure to dissolved pHs to resident fish species. The data showed that the lighter pHs dominated the contaminant profiles and were the ones most susceptible to downstream transport. And you can see that from all the peaks in that first half of the chromatogram there. Although the samplers were used in the study as part of the response, this is a case to where samplers like this could also be useful during assessment and restoration phases, as they can evaluate changes in chemical concentrations over time, especially as the chemical concentrations continue to fall to levels that may be more difficult to measure with a traditional grab sample. Again, looking at oil-related issues, the Norwegian Institute for Water Research, or NIVA, conducted a study using SPMDs and POSIS in the North Sea to determine the extent of contamination from petroleum hydrocarbons as well as alkyl phenols in produce waters from offshore oil platforms. The samplers were deployed at intervals up and down a gradient based on the prevailing currents around the platforms. Short chain alkyl phenols and lighter pHs, typically the alkylated naphthalenes, phenanthrines, and dibenzothiophenes, were consistently measured within 1 to 2 kilometers of the discharge point. While the concentrations measured were typically less than 50 nanograms per liter, which was orders of magnitude lower than levels reported to give acute or sublethal effects, there is always a potential for long-term consequences, which are currently unknown. Early on, I talked about some extreme uses of samplers as far as extreme conditions. Typically, we think of passive samplers as a tool to be used in relatively shallow waters for periods of weeks to months. This example was by the Royal Netherlands Institute for Sea Research, where they investigated the potential of passive sampling techniques to measure organic contaminants at deep ocean sites. They deployed SPMDs at depths up to 5 kilometers for periods of 1 to 1.5 years at sites in the North Atlantic Ocean and Indian Ocean. What they found was concentrations of pHs, PCBs, hexachlorobenzene, and DDE were measured across all the depth gradients. The data suggested that evacuation of surface waters down to a depth of about 1 kilometer was an important mechanism for contaminant transport into the deep ocean. Probably to me, the highlight of this whole study was it showed that although it was extremely challenging, it is possible to use passive samplers in some of the more extreme conditions that we would have on the planet. An example of linking the chemistry to the biology was a study that we did using SPMDs and POSIS, where they were deployed at 69 sites over a 2-year period in tributaries across all 5 of the Great Lakes. 150 of the 184 chemicals targeted were detected at least once, and typically, as you would expect, were highly complex mixtures of chemicals. The chemical data was then entered into the ToxCast database from EPA, which contains toxicological information from hundreds of assays for over 9,000 chemicals.
Bar graphs with chemical breakdowns for each of the 5 Great Lakes: Superior, Michigan, Huron, Erie, and Ontario. Michigan and Erie have the most results. Chemicals found include herbicides, fire retardants, PAH, detergent metabolites, plasticizers, and other.
Information we was able to get back from ToxCast allowed us to calculate the ratio of water concentrations and the activity concentration from those ToxCast assays to determine exposure activity ratios, or EARs. As you can see in this figure here, EARs were estimated for each chemical, and then we could use that data to rank the cumulative potential of chemicals present that may elicit some sort of biological response. As you can see pretty easily, sites around Lake Michigan and Lake Erie tended to have the highest risk to aquatic organisms. High EAR values indicating greater potential risk for many chemical classes tended to be correlated with urban land cover and areas that received high amounts of wastewater effluent influence. But as you moved into the more rural areas, you saw different responses that tended to be linked more to herbicides as well as flame fire retardants. The last case study I want to show here is looking at metals. In this case study, metals were sampled using the SLMD to measure concentrations in a large river system that received mining waste. In this example, as you can see in the lower picture, the SLMD was embedded in a rock, which then was lowered to the bed sediment. The rock allowed the sampler to stay in place, as well as maintained the sampler positioning on the sediment to be able to measure what that metal concentration was at the sediment water interface. As you can see from the data figure there on the right in the red circle, concentrations of copper in this case at this particular site did tend to fall within a suspected effects range. So it was a good technique to try to measure potential risk to organisms at a particular level of the river system. So to sort of wrap this up, there are a lot of established methods for sampling chemicals from the environment. The body of work over the last few decades has demonstrated that passive sampling techniques are a viable option for providing data on dissolved concentrations of chemicals in the environment. The types of passive samplers available for use and the body of knowledge surrounding these samplers is rapidly expanding. Therefore, when you go to select the type of passive sampler, you need to make sure that that particular sampler can answer the question of your study, because not all samplers are developed to the same level. And remember, although informative, passive samplers provide information that should be considered complementary to other sampling techniques. So again, a grab sample is not a passive sampler and vice versa. In 2010, a fact sheet was prepared by USGS to provide basic overview of using SPMDs to sample oil spills. This fact sheet also provides some practical considerations to aid users in designing their studies. Also shown here is a how-to guide we put together back in 2010 that provides tips and items for consideration for using passive samplers. This guide is sort of a cradle to grave, everything from designing study to going to the field to picking a laboratory to understanding your data. It is tailored towards the SPMD and POSIS, but the information presented in here is largely applicable to about any type of passive sampler you may choose to use. With that, I'll thank you for attending today, and I'm happy to answer any questions you have in what little time we have left. And my contact information is on the screen there if you would like to reach out to me with more questions in the future.
David Alvarez. USGS Columbia Environmental Research Center, D. Alvarez at usgs.gov, 573-441-2970.
Thank you.
Thank you, David. If you're interested in asking a question, you can come off mute or use the raise hand function. As we're waiting for that, Dave, quick question. Can you comment on price point? I mean, I know PAH analyses can get quite costly. Any brief comment you can make in terms of price comparisons?
Every sampler's definitely has got its associated cost. You know, I think if all you needed was like one sample point, then a grab sample is obviously going to be cheaper than a passive, because the passive, you got all the hardware and everything that goes with it. If it's something to where you're going to need to sample over time, then the passive is going to be much cheaper, because in the end, you only got one analysis. And the reality is the analytical end is where all the money goes. So I think the samplers are nowhere near as expensive as what people may think they're going to be. And everyone's got different options and prices. Many samplers are commercially available. I think the price point could be all over the place, so kind of hard to really say.
Thanks. Yeah, so if you have a question, you can come off mute. And there's also some resources that Dave had mentioned on his slides that are also in the chat that you can link to directly.
Hi, this is Jeremy Buck. Just a question on if you can comment on differences in deployments in marine versus freshwater versus estuarine, brackish, and if there's a need to kind of make adjustments for any saline conditions differences.
There's always exceptions with certain chemicals that may behave differently, but for the most part, from what we've seen both in laboratory studies and field studies, there's not really any noticeable impact on the performance of most samplers, especially things like SPMDs or the PEDs, things that are going more for those hydrophobic regulated contaminants. We do see differences, and this is probably more in brackish water, and I'm not a marine guy, so I have no way of knowing how to predict, but some sites you just get a lot more growth of stuff. I mean, we've had deployment canisters that have come out of some sites that were so full of the inside of barnacles that we literally was chiseling out our samplers. And then we have other sites that come out and they are crystal clean and look like they've never been deployed. So, I have no idea how to predict that, but as far as performance of the samplers, I would not expect that you'd have any real considerations.
So it's a more of a difference in potential fouling conditions that you
Yeah.
encounter.
I would say it's more on the logistical side than sampler performance.
Okay, thanks.
Well, not hearing any more questions, I just want to thank Dave once again for your presentation, and we will get that posted. And I will also put, or Dave, maybe you can just drop your email also in the chat so it's readily available for folks in case they do have follow-up questions for you.
Yeah, I'll do that right now.
Wonderful. Well, thanks everyone. Have a great rest of your day, and we hope to see you next time.
Thanks, everybody.